We wrap up chapter 4, get into some chapter 6 and all that good stuff. So last time there in chapter 4, we got into electron configuration. And remember that electron configuration basically shows us where all of the electrons are in the atom and where they're housed. And as we talked about, they're basically housed in these what are referred to as orbitals. And there's a few different types of orbitals that we talked about. There are s orbitals, p orbitals, d orbitals, and f orbitals. And remember that any individual orbital could hold a maximum of 2 electrons. So any individual orbital could hold a maximum of 2 electrons. Now, in terms of these orbitals, they start at different energy levels, and remember that the energy levels are represented by that N sort of symbol, and that represents the principal quantum number. And again, just a fancy way for energy levels. And on the first energy level, that's really where those s orbitals start. And you'll have s orbitals on all the other energy levels as well. There's only one type of s orbital, and that means that the maximum number of electrons that you could put in any s orbital on any level is going to be 2 electrons. Now, p orbitals don't start until you get to the second energy level. And unlike s orbitals, there's actually 3 different types of p orbitals. And again, since each individual orbital could hold 2 electrons, that means if you filled up, as we talked about, what is referred to as the subshell, which is basically a grouping of the same type of orbitals on the same energy level, that would get you 6 total electrons. D orbitals don't begin until you get to the third energy level. And d orbitals, there's actually 5 different types of d orbitals in this subshell. So a grouping of 5 d orbitals on the same level makes up the d subshell, or sublevel, sometimes referred to. And since there's 5 times 2, that means if you maxed out that subshell, you would have 10 electrons that you could put in there. And lastly, on the fourth energy level, that is where we first start to see the f orbitals appear. And there's actually 7 different types of f orbitals. And once again, since each one could hold 2 electrons, that means if you maxed out that subshell, that would get you 14 electrons that you could do. So that's a really important thing to remember, basically how many maximum electrons that you could put into, say, an s orbital, a p subshell, d subshell, or an f subshell. Remember as well that you don't necessarily need to fill them always, but that is sort of the maximum number of electrons that you can put in there. There's also, as we talked about, a really sort of special order, if you will, in terms of the way the electrons go into the atom. And it is a little different than you may think. Again, we do see some differences in terms of energy levels of these different orbitals that we have. And that's going to affect the electrons going into the atom, as the electrons always go in from the lowest energy to the highest. So they just kind of fill the bottom energy and keep filling from the bottom up until they're done basically filling electrons. So there was that little chart that you can make really easily, and we talked about how to make it. So one more time, basically, this column is really a good thing to know. So you know that S's start on the 1s, and again, if you go down to the right a little bit, P's start on the 2, D's start on the 3, and F start on the 4. So if you just kind of go diagonally down there, 1, 2, 3, 4, at this point, all you have to do is just fill in the numbers underneath, basically up to 7. You could even go 7 on all of them. It really won't matter. You won't get there anyways. But if you can't remember where to stop, you can. So you just fill in the numbers with the same letters underneath. Again, going to pretty much 7. Then you take here 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d. Really, we stop at 6 because we don't need any more, and really F stop at 5. But like I said before, if you put a couple extra numbers down this way, it's not going to make a tremendous difference. Again, you probably won't get there because You only need up to like 5F there for what's on the periodic table. So you really don't need to go any further than that usually. And at this point, again, we just kind of draw our arrows. And now we have, again, our order at which this goes. And here are 3P to our 4S as we talked about, to our 3D, 4P, 5S, again, to the D and so forth, continuing on. So that's a really good way to remember the order correctly. It is something that you can basically just make yourself by just remembering that way. And then just go down again with just 1 through 7, basically, in this case. We always start here at the top, right? So we always start every time when we write electron configuration up here at the top. We come through, we fill, and then we zigzag back, come through, fill, zigzag back, and come through and kind of keep filling in that method there. When we write electron configuration, remember, if you're writing for something that is neutral, the atomic number, which is the number of protons, will equal the number of electrons. So I think we did a few at the very end there. For example, like hydrogen has 1 proton, should also have 1 electron. And for hydrogen, that is a 1s1 is the electron configuration for it. The first number here is the N number, that principal quantum number, the energy level. That is the orbital that the electron's in, or the subshell it is in. And the one on top in this example is the number of electrons in the orbital or subshell. So again, that is what each of those sort of parts of the electron configuration means. We did helium as well, which is 2 for protons, 2 for electrons. Again, starting at the top there, 1s2. And again, if we were to kind of look at that 1s orbital, we would put 1 electron in and then another. That is 2 electrons if those arrows represent the electrons. And at that point, we are full. And we would need to then come back around this way. And then that would take us next to the 2s, as I think where we left off last time with lithium, which has 3 electrons, 1s2, 2s1 in this case. And what this basically means is, again, the first number is the energy level. So on the first energy level, we basically have 2 electrons. In this case, on the second energy level, we have 1 electron that's hanging out in the s orbital. Yes, sir. I would prefer you to write it like this. Yeah, so she's like the only book I've ever seen write it that way. She just throws out numbers like, 2, 4, 6, 8, who do we appreciate kind of deal. And that is it's probably the only book I've ever seen kind of do it that way per se. So this is really the proper way to do it. And for lecture and everything, you should write it that way. Now, with that being said, clearly the homework's based off her book, so you may have to do the homework in that sort of method, and it's based on the maximum number of electrons you can put on each of the levels and shells, basically. Yeah. So yeah, so basically everybody on that energy level, you combine the numbers, basically. Yeah. But definitely for here in lecture, you should write it like this in quizzes and exams. But like I said, it's probably the only book I've ever seen kind of write it that way. She never used to years ago in her old books. She used to write it like this, but then at some point, like maybe 7 years ago or so, she changed to kind of go into that sort of format. So we will write electron configuration like this, but again, follow how it says online for the homework, obviously. Yeah. Other questions? Okay. All right. So with that being said, let us continue on here. And we did lithium, so might as well continue on. We'll do number 4, which is should have 4 on. Once again, here we're going to start at the very top. So I'll just kind of remake that real quick here. Kind of do the front part there. So we will start here. So that is again going to take us. At that point, we need to zigzag back around and come back through here to our 2s2 at this point. And again, that is the way you should write it. Like I said last time, is no weird things. And it should be a big one, a lowercase sort of letter, and a superscript up on top for that. And again, if we count up the top numbers, that is the total number of electrons we distributed in the orbitals, and that's 4, which is obviously what we need. At this point, we now have 2 electrons on the second energy level, and we now have 2 electrons on the first energy level in this particular case. If we continue on here, at this point, we could also see, if we're just kind of looking at a little diagram picture of what's going on, we have filled the S, we have now filled the 2S. At this point, for our next ones, we will have to come back around and head over here to our 2P in this case as we continue to fill it. At this point, that would be boron, which is 5. So that's 5 electrons. Again, we always start up here at the top, always. And that's going to give us 1s2. Again, coming back around to 2s2. And now in this case, 2p1 only. Again, we count up the top numbers there. That is 2, 2, and 1, which is 5 electrons have been distributed if we just count up these numbers. At this point, how many electrons do I have on the second energy level? And 3 electrons there on the second energy level. Well, I have, remember, the only orbital is maxed out at that first energy level. Now again, diagram here, which is sometimes referred to as an orbital diagram. And if we distribute, if these lines represent orbitals here, we would have an electron there in our 1s, we'd have an electron there in our 2s, and now we would put an electron here, really on the left here in this case. And you can see at this point, we actually have 5 more spaces for electrons here in this subshell before we are full. And the first 10 here, which is number 6. Again, that would be starting up here at the top. We're going to go 1, 2, 2p2 in this case. We now have, again, 4 electrons on the second energy level, and we still have our 2 on the first energy level in this case. And I'm just going to kind of add to my picture here, just for how these actually do fill. They actually would go into 1 orbital at a time, an electron, before they start pairing up. So they'll go in 1, have a, they come up until it's all full, which is nitrogen. Here at top, we have 1, 2, 2s2, 2p3 at this point. And again, if we look at the top numbers, 2, 2, and 3 is 7 electrons. So we've filled 7 electrons. Again, that 7th electron is actually going to go. So each one of these lines represent, if you remember, there's a px orbital, a py orbital, and a pz orbital. There's 3 different individual p orbitals there, and each of those other lines represent that. At this point, if we go to oxygen, which is number 8, continuing on, starting again, 1s2, 2s2, 2p4. And again, if you count up the top there, we got 2 and 2 is 4, plus 4 more is 8. At this point, in terms of the second energy level, we actually have 6 electrons there on the second energy level, and still our maximum 2 electrons there on the first energy level in this case. By the way, at this point, I have nowhere else to go. We go back to the left, and we go in the opposite direction. That's what is referred to as being paired spin. Electrons have spin, and they have quantum numbers, which is not important for our class, but that's how they basically go in. That's why one goes up, one goes down. In the paired position inside an individual orbital, what's known as Pauli's exclusion rule, which is a rule that says they can't go in basically the same way. Basically, that's going opposite way. Not so far. Continuing on here, number 9, might as well. That is fluorine. And fluorine, which is 9 electrons. So again, starting at the top there, 1s2, 2s2, 2p5. And again, that next one would actually go here. How many more can I put in that subshell until it's full? One more, right, until it's full. So that orbital there at the end, basically the PZ orbital has room for one more electron to go in. And that happens with our friend neon here at number 10. 1s2, 2s2, 2p6 at this point. And now we are full. Now has 8 electrons, right, on the second energy level and 2 on the first. By the way, after that, where do I need to go next? I'm here. That means I then need to go to the 3s, right? And we've now maxed out the second energy level in terms of electrons. We got a grand total of 8 hanging out there. So in terms of the earlier, I think in the books you would do something like 2, 8, right? Or something like that would be the electron configuration for that. Question on that there. Okay, so why don't you write the electron configuration for, why don't you do argon, which is 18 on the periodic table. So again, here we're gonna go 1s2, 2s2, and then obviously here we're coming around, and then now we got to come back this way to our 2p6. That obviously is 10 electrons if we count the top, so we got 4 to go. We got to continue on now to our 3s, which we could put a maximum of 2. So counting up the top numbers, we're up to 12. We still need to go, so we got to zoom back around here and hit a 3p6 in this case here. And again, at this case, now have 8 electrons on the third energy level, right? 8 electrons on the second energy level, and still our 2 electrons there, first energy level. Question on that? Yeah. You will not. So that's why I should make. No. Yeah. So yeah. So and you just want to make it like we talked about there, kind of do 1, 2, 3, 4, and just put the number straight down, and you can make it. That's like yeah. All right. Another question. All right. Look at let's take a look at number 19, which is potassium, which I think is what you got going on. So if we look at potassium, we got 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1, right? So as we just saw a second ago, if we take this part of the configuration here, that is 18 electrons, as we just saw. If we count up the top numbers, that's basically 18 electrons. On the periodic table, number 18 is the one we just did, which is argon, right? So we can write a kind of abbreviation, if you will, a shorthand, and we could put in like little brackets argon. And what that basically indicates is the electron configuration for argon, and we can continue on and give us 4s1. Question? Yeah, so again, that is the order that we were talking about where you make that chart. What actually happens when you put a lot of electrons in is the 4s orbitals are actually lower in energy than the 3d orbitals. And that means that the 4s actually gets the electrons first. So that's why, again, it's important to know that little chart and how to make it, because that will give you the correct order at which they go in. They actually don't go in order when you do filling order like we're doing electron configuration. And that's very common. The S's come before the D's, basically. Not to confuse things, but actually what happens, as we'll talk a little bit about probably, once you start actually putting electrons into the D, they actually do switch in terms of their energy, but that's only after it's filled and start doing that. So beforehand, the S is lower than the D, but then actually It does a little switcheroo when it's all said and done. And that actually affects, for example, transition metals and those guys that have d orbitals when they lose electrons, which ones actually get lost first and stuff like that. So, but when it goes in, the s's are lower than the d, so they do get the electrons first. Yeah. Other questions? Hold on. So this is a shorthand. Argon is what type of element on the periodic table? It's group 8, which means it's a noble gas. Yeah. And that is what needs to go into the bracket. Going to do this sort of shorthand is sometimes referred to as noble gas configuration in a sense. It has to be the noble gas here, group 8, that comes right before the element you're doing it for. So obviously here, argon, potassium's over there, and argon comes before. When I say right before it, but for example, if we were doing zinc, we would also back up to argon. If we were doing, for example, aluminum, you would back up to neon. So it's the noble gas that comes right before whatever element you're writing. So for example, if we looked at sodium, which is 11 electrons, it would be 1s2, 2s2, 2p6, and a little 3s1 action. And right about there, that is 10 electrons, which is our neons configuration. And we would continue on with 3s1, just like if we were doing iron, which is 26. You would go 1s2, 2s2, 2p6, 3s2, 3p6. Now again, following that chart, if you follow the chart with the arrows, here again we go 4s2 first, and now we go to the 3d. So if you're following along there, I don't know if I got it on that side. I do, I think. So we come through here, 3p to 4s, and then we zig back to our 3d. So again, that will give you the proper order, having that chart. And I think you should probably write it the one. 3d6 there would be our irons configuration. Now for iron, if we back out to right about there, that is 18, which is still argon. So we could go argon, 4s2, 3d6 would be the shorthand. So again, it's always the noble gas that comes on the periodic table before whatever element you're trying to write it. If you want to shorthand it, again, noble gas configuration is sometimes referred to, has to be a noble gas that goes in the brackets. Any questions on that there? You could write electron configuration either of those two ways, unless it says not to use noble gas configuration, then you should write it as 1s2, and so forth, 2s2. Yeah. The purpose of that is, as you can see above with irons written out, long, it's short. So it's basically, it literally is like a shorthand, and basically. Yeah. Yeah. It really is sort of a shorthand, and, it just makes it a little bit easier to see sometimes. And there's sort of a benefit as well. We'll talk about in just a second when we kind of look at something else as to why sometimes people will do that. Yeah. As long as like don't use noble gas configuration. If I just said, give me the electron configuration, you could write either way, but not the 2, 4, 6, 8 way. So you got to do one of those two ways. Other questions? Okay. All right. So why don't you try, why don't we do, first off, any questions on electron configuration? No. Okay. So let me find that picture actually, I think. All right. I want to go there real quick. Okay, so let's just talk a little bit about periodic table and electron configuration. And you actually can count off on the periodic table electron configuration. I don't know if I would recommend it per se for certain things, but you definitely could do it. So when we look at the periodic table, we have basically 7 periods, right? And these periods represent our energy levels. And we have our groups, right? So we have group 1 and 2, which is here. And this is our S group, our S block is sometimes referred to. And I don't know if I like this periodic table. Let me see if I can find a better one. Hang on a sec here. Do I have a better one? Actually, I'm going to steal this one for the time being. All right. I like this one better. All right. So we're going to steal this periodic table here. So we got 7 periods. And again, periods go left to right. And those are the energy numbers. Now, the first 2 groups on the periodic table is the S block. And for S's, you can put how many electrons? You could do 2. So 1 and 2, basically. Now, groups 3 through 8 is what's referred to as the P block. And for the P subshell, you could do 6 electrons. So 1, 2, 3, 4, 5, and 6. And this is the transition metals here. And transition metals is the D block. And you could put 10 in there, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I don't have it on this periodic table, but over here in the real periodic table, we have these 2 rows at the bottom, and that is the F block. I won't count it, but if you count from this guy to that guy, that's 14 spots, basically, right? So that's 14 on the bottom. So S block over here, group 1 and 2. P block over here, 3 through 8, D block. And again, I'll just kind of sketch it here. This is our F block down here, those 2 rows on the bottom of the periodic table. So you could actually count off the electron configuration if you do know what you're doing. So for example, we just did sodium, which is right here. So if I were to count off my electron configuration here, let's get rid of some of these markings. All right, so we're going to start over here. This would be 1s2 over there to helium. This is now 2s2 to there. This is now P, but it's on the second, so that's 2p6 to there. Now to sodium, that is 3, and it's 3s1. We just take 1 box in, and that is the electron configuration for sodium, just counted off the periodic table there. Now, if we did, for example, iron, if you will, right? Actually, let's not do iron yet. Let's do sulfur, for example. We'll go to sulfur here. So let's say we wanted to do sulfur's configuration. Again, we would start at the very top there. And you would go 1s2 to the end to helium. So I'll write it there. 2s2 to there. 2p6 all the way across there. Again, 6 boxes basically. 3s2 right there. And now this is 3p. 1, 2, 3, and 4. 3p4 would be the electron configuration for sulfurs. So you could literally count it off the periodic table, again, if you know what you're doing. And I say if you know what you're doing because let's now go to iron, which is... You want a periodic table? Yeah, I imagine you'd get one. It does. That's just the first exam. It's just a blank periodic table. Fill in everything that you know. No, I'm kidding. No. Although I do know somebody that gave that as a final one time in a class. I'm like, wow, I think I would fail that class. So that was the end of the year. Like, here's just a blank periodic table. Fill in everything we learned about everybody. I'm like, oh, geez. All right. So that wasn't me, by the way. So you will get a periodic table. It will be provided for you. You get to use my periodic table. It will pretty much look like this. Yes, a lot smaller, I imagine. Yeah, so it will have all that information. It will not have names or anything on it, obviously, and stuff like that. All right, so let's get to iron here. We're going to do iron, and we'll go this way. So again, with iron, we're going to do our 1s2 to helium, our 2s2 there, our 2p6 to the end, our 3s2 to there, our 3p6 all the way across, Now we're on number 4 here. That is 4s2 to calcium. I'll just go up this way. Now this is D. Yeah. What energy level do D start at? They start at 3, even though it's on period number 4. This right here is 3D. Underneath it is 4D, 5D, and 6D. The D's are actually one behind the period number. Yeah, so that's why I say you got to be careful, because you don't want to roll 4D here, because it would be incorrect. So again, you got to watch out for little things. But if you do know that's 3D, that would be 3D1, 3D2, 3D3, 4, 5, and 6. A little 3D6 going on there. So you do have to be careful in that transition metal region, as it is, again, one behind. And the 2 rows on the bottom here, technically, right, go up into here. And that's actually 4F and 5F, those 2 rows on the bottom, which means they are actually 2 behind the period numbers as well. So it gets a little crazy if you're trying to count it off on the periodic table for those guys down on the bottom. And again, in the transition metal region, you do need to be careful. The upper transition metal region, you'll be okay if you just remember 3s there and not 4. But again, as you start getting into this area where all those guys are together, I highly would not recommend reading it off the periodic table, because you probably will make a mistake. If you do the little zigzag guide that we learned there, you probably should get it all correct in most cases. Any questions on that there? Now, a couple other things about electron configuration, and I'm going to head back to where it was, I think, maybe. That looks good. That looks empty. Let's go there. Why not? All right. So when we talk about electron configuration, there actually is a number of exceptions in terms of kind of how the electron configuration actually is. And the things that you're responsible for is chromium, which is number 24 on the periodic table, and copper, which is 29 on the periodic table. It is these 2 right here, chromium and copper. So right here in the first row, transition metal region. Now, if you were to follow the zigzag way, you would end up with, for chromium, this configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4, or if you shorten it down there, argon, 4s2, 3d4. For copper, if you did copper following the kind of way we talked about there, you will end up with this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9, or again, if you shorthanded it, argon, 4s2, 3d9. Now, where the exception actually occurs is actually at the end here. Now, earlier there was a question about the 4s and the 3d orbitals. Now, in terms of energy, as we talked about, the 4s is lower in energy than the 3d. So we do get the electrons to come in here first, but they actually are really close in energy, to believe it or not. And it has been found sort of experimentally that the chromium and copper are actually more stable with 1 extra electron kind of promoted up to the D. So one of these electrons basically works its way up to the higher energy level. There's actually some benefit to that that's a little outside of our class, but one of the benefits is it maximizes like parallel spin of those electrons. They're all kind of heading in the same direction for chromium. And it also pairs up everybody there for copper. So the correct sort of electron configuration for chromium actually should be, I'm just going to do the shorthand, argon, 4s1, 1 less electron there, 1 more electron there in the D. And again, that kind of fills up all the D's there for chromium. And again, we have this guy gone. So maximum, that's what's referred to as parallel spin, everybody heading in the same direction in terms of those electrons. Now, this would be the proper one for chromium. And for copper, it's the identical sort of exception. It is argon, once again, one less electron in the S, and it's been promoted up there to the D, and it would be 3D10, and that would be the correct electron configuration. These would be technically incorrect. So there are a number of exceptions like that on the periodic table, but for our class, it is just chromium and copper that you need to worry about. If you actually go below chromium on the periodic table and you go below copper on the periodic table, kind of go down on each side and in, there's a ton of exceptions like that. For example, silver is an exception. PD actually has no electrons in the S. They've all popped up to the D. So there's a lot in this area, kind of below those two on the periodic table, that have very similar sort of exceptions. So I would say in reality, there's a lot more exceptions, but for us, you don't have to worry about it. You just need to worry about chromium and copper. But if you do come across some, maybe in a book or something like that, it is correct. There are more exceptions in this area, but we're just not going to worry about them. So for us, chromium, copper, you're responsible for. You need to write correctly like I boxed here with the extra electron up in the D. Even though there are really more exceptions in this area, if you get something like silver, for example, you could just follow our little zigzag thing and write it the way it is. Any questions on that there? Yeah. Now, in addition, first off, any questions on electron configuration? Now, let's just talk, since we've talked about ions before, what happens when something maybe gains a charge and how the electron configuration is affected by that. So let's just say, for example, we had aluminum. And aluminum will typically have 13 electrons. Aluminum will typically make a +3 charge, which means how many electrons should that guy have? Plus means I gained or lost electrons. And how many did I lose in this case? The number is 3, yeah? So if neutral has 13, the one with +3 should have 10 electrons. So if we were going to write the electron configuration for our aluminum, it would be 1s2, 2s2, 2p6, which is 10 electrons. By the way, who on the periodic table again is 10? That is neon, right? It's the same electron configuration basically as neon. Now, if I took something like oxygen, with no charge, it has 8 electrons. When oxygen makes a charge, it makes a -2 charge. Minus means it actually gained electrons, right? And it gained 2 electrons, which means oxide here, which is this oxygen, actually has 10 electrons as well, which means if you're writing an electron configuration for this guy, 1s2, 2s2, 2p6 are neon's configuration as well. All three of those things, neon, aluminum with a +3 charge, and oxide or oxygen with a -2 charge, they all have the same electron configuration. That is what is known as being isoelectronic with each other. Isoelectronic are things with the same electron configuration. And that is typically what happens with our representative elements when they gain a charge. The guys on the outside, not transition metals, but the guys on the outside, non-metals and metals, they typically will end up at an electron configuration like neon, which is a noble gas. Noble gases, are they stable or not really stable? They're super stable. And as we'll talk about in the next chapter, that is really the whole purpose of any bonding that you talk about, is for everybody to basically end up like a noble gas in terms of their electron configuration. How metals and nonmetals do it is nonmetals will actually gain electrons and go forward in their electron configuration and end up like a noble gas. Metals will lose electrons, aluminum back, and end up back at a noble gas. And that allows everybody to have the same electron configuration as that noble gas, which is super stable. And for example, with metals and nonmetals, that's what an ionic bond is. That's really the whole purpose of an ionic bond, and a covalent bond as well. Any type of bonding is for everybody to achieve the same electron configuration as the noble gases because they're extremely stable. So that creates obviously very stable bonds. Double jeopardy question is, does aluminum in this case and does oxygen become neon? They do not. Why do they not become neon? That's exactly right, right? What we talked about is as long as the protons don't change, we don't change the element. So here what we're talking about when they become like neon in this case is they're becoming the same electron configuration as neon, and that creates a really stable thing. They don't become that element because the number of protons don't change. Any questions on that there? All right. So let's just say you had phosphorus with a -3 charge. Why don't you write the electron configuration? And let's say you had lithium with a +1 charge, right? The electron configuration. So phosphorine, again, neutral phosphorus would have 15 protons and also 15 electrons. Phosphide, which is phosphorus with a -3 charge, means it has gained 3 electrons. So that goes from 15 plus 3 is 18 electrons this guy should have. And that's going to give us 1s2, 2s2, 2p6, 3s2, 3p6, I think in that case. And that is, as we've seen, argon's configuration, right? So again, phosphorus is going to go forward on the periodic table, right, and hit argon's configuration in terms of its electrons when it gains it. And lithium here has 3 protons, which means it would have 3 electrons. +1 means it has lost 1 electron. So that is a lonely 2 electrons it's got left. And that will give us a 1s2. Or that is our helium, which is a noble gas as well, right? So that is our helium in that case. Any questions on things with charges? So anybody on the left-hand side, right-hand side, they typically will end back out at the noble gases. Transition metals are actually a little bit different in terms of what happens with them. And it has to do with that kind of 4s, 3d, the S and D relocation. So we looked at iron before, for example, which was 26. And that was our argon 4s2, 3d6 in this case. Now, because as I mentioned before, that 4s in terms of energy is lower when the electrons go in there, they would feel something like this. We would put our 2 electrons in there, and then we would put our 6 electrons up into that d orbitals. Now, what's going to happen in this case when iron, for example, makes a +2 charge, it is going to actually lose 2 electrons. But what happens before that is, as I mentioned before, once you start populating the d orbitals, they actually switch in energy. And what happens in that case is you actually end up with the 4s orbitals now actually being a little bit higher than the 3ds. And again, that is opposite of the way that it is filled. This only happens after you start filling the d orbitals with some electrons. And this affects it because when people lose electrons, they typically lose their highest energy electrons. And in this case, at the end, the highest energy electrons are actually the 4s ones in this case, right? And when it will lose these 2 electrons, 26 electrons to lose these 2 electrons. And the configuration for this guy would actually be argon 3d6. We would actually lose the s electrons first in this case because they actually do end up being higher. But when the electrons go into the atom, they're actually lower. So there's that weird kind of switch thing that happens with the transition metals. By the way, iron could also make a +3 charge, which means if I took out the 2 electrons here in the s, I now need to lose 1 more electron, right? What is left at that point? We now have to go into the d, and we have to take an electron out of there. And now we will end up with argon 3d5. 2 from the 4s and 1 from there. And that would give you the electron configuration for a transition metal. So transition metals, as we just talked about behind this chair, these are the transition metals, right? In that transition metal region, all these guys over here are the S block in group 1 and 2. these transition metals will always lose these S's for they'll go into the d orbital there to take them out. And they don't actually end up, those transition metals, as a noble gas. And that's because they have a lot of valence electrons, a lot of outer electrons. For example, something like zinc would have to knock off about 12 electrons to get back to a noble gas. And usually it's not like a zinc plus 12 type of thing happening there. So it doesn't usually happen for our transition metals. They actually don't end up usually back at a noble gas configuration. Just our guys on the outside always kind of end up back, either forward or back in terms of metals at a noble gas configuration. So for example, if we did nickel, why don't you try nickel with a +4 charge? Nickel normally has 28 electrons there in a neutral situation. So what would the electron configuration be? And again, nickel is right here in the transition metal region. Okay, so let's take a look, see how you're doing. No charge is 28. If we were again going to kind of write the electron configuration a little shorthand, so not to write it all out, we got a 4s2, a 3d8 happening there. Again, 4s2, 1, 2, 3, 4, 5, 6. They're at the 3d. Now with a +4 charge, that means nickel with a +4 charge has how many electrons? 24 electrons, right? Plus means we lost. 4 is how many electrons we lost from the neutral guy, which was 28. Now, again, because this is a transition metal, we got basically this situation happening here. So our higher energy electrons are going to go first, which are our 4s, but that's only 2. We then need to also take out one there and one there, and that's going to leave us argon. These guys are gone, and we're going to take 2 out of there. 3d6 would be the electron configuration for nickel with a +4 charge. Again, with the transition metals, they kind of lose electrons a little bit different. Everybody else that's not a transition metal, for example, that's a metal, when they lose electrons, it's the last things in the electron configuration. Here, it's not going to be the last ones in the electron configuration, but it will always be the S's first, and then if necessary, they'll go into the D's. Any questions on that there? All right, let's take a break there, 5 minutes. Questions on electron configuration, anything we've been talking about? Obviously, you need to be able to write electron configuration. And again, like we talked about before, you do need to know the order, the correct order, again, with the S's before the D's. And again, with things maybe with charges and without charges. I don't anticipate too much transition metal with charges, but maybe guys on the outside with some charges. You might need to write some of those guys. Any questions on it? All right, we're going to finish up the last part of this chapter here, really talking about sort of periodic trends. And that's going to help us as we get into the next chapter. We talk about sort of bonding and all that kind of stuff. Understand why certain things sort of occur. So one of the first things that we're going to talk about here is valence electrons. And valence electrons are the outermost electrons. They are the ones that are in the highest energy levels. So for example, here we have our nitrogen, which is 7, and we have our 1s2, 2s2, 2p3. And again, remember that these first numbers here are the energy level. So as we were talking about, as we were kind of doing it, we can see here on the second energy level, which is the highest, there is a grand total of 5 valence electrons. So that is what's referred to as the 5 valence electrons for nitrogen. These electrons here that are on the lower energy level, they are what are referred to as core electrons. And those are the core electrons which are pretty much closest to the nucleus. So they're like right there at the nucleus. The valence electrons are really important because they are essentially the outermost electrons, and they are the ones that are involved in bonding. So when we talk about bonding and all that kind of stuff, It is really the valence electrons that are essentially the ones that are involved. Now, you could look at, for example, we did potassium, right, which is 19. We had a little argon, 3s1, R1s2, 2s2, 2p6, 3s1 there. Did I say 3s1? That's 4s1 would be better than 3, I suppose. 3s2, 3p6, and 4s1. There we go. So it's like 3, but one more. There we go. So here it's actually this guy right here, that 4s1 electron is our valence electron. So you could definitely write out the electron configuration. As you can see, that guy's on number 4. These are 3, these are 2, and 1. To figure out the valence electrons, but nobody wants to do that. So that's why we have a periodic table. So the number of valence electrons in stuff is equal to the group number on the periodic table. So when you look at the group number on the periodic table, potassium's over there in group 1. It has 1 valence electron. We did nitrogen, which is over here in group 5. It has 5 valence electrons. Oxygen, which is group 6, means it has 6 valence electrons, 7 valence electrons, 8 valence electrons, except for who in group 8? Doesn't have 8 valence electrons. It's helium because it only has 2, so you can't have 8 if you only have 2 total, right? So that's an exception there, obviously, since it has only 2 electrons total, helium, so it would have 2 valence electrons. Everybody else in group 8 will have 8 valence electrons. That's much faster than, writing out the electron configuration if you need to figure out how many total valence electrons there are. So carbon there, group 4, 4 valence electrons, aluminum, group 3, 3 valence electrons, and so forth. What about our transition metals? Well, our transition metals, when you're looking at it, I'll just kind of sketch one, maybe like a bad periodic table over here. So this is group 1, this is group 2, and our traditional 3, 4, 5, 6, 7, and 8, right? And that's our A numbering, right? That's how we go. And here's our transition metals here. And when we look at the transition metals, we actually want to look at the kind of 1 through 18 numbering. And that means if we were kind of doing the 1 through 18 numbering, this would be 1, 2, and then we just roll 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 as I almost run out of room. So going from there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And that is what we want to think about for our transition metals. And that's because, for example, right here is iron that we've been talking about, right? Which is a transition metal. It is group number 8, not that 8. So this is the kind of 1 through 18 numbering, or 8B, if you will. So that is group 8. And if we write again the electron configuration for iron, as we saw there, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, and 2, 4, 6 as well. 6 there. And when we look at it, remember that these are the highest energy levels, as we were just talking about when it loses electrons, right? It has that 4s and 3d, and that's basically 2 and 6 is 8. So because the transition metals have always those s electrons that are actually the highest energy level, and they also have the d available to them, they can have upwards of like 12 if you get down to like zinc over there. So we use kind of the regular numbering for that, kind of 1 through 18. But remember, if you come back this way, you got to switch back to the A numbering. And this again is group 3, 4, 5, 6, 7, and 8 as you go that way. So I would say just for the transition metals, you can think of it as like 3 through 12 if you want. And that is basically the way you could do that. The good news is, for the most part, outside of probably a lab question, we're not going to worry about valence electrons on transition metals, so you don't have to worry about it. But all the representative groups, the kind of A numbering outside the transition metals, will equal the group number as well. Any questions out there? Yeah. Yeah, it's just a numbering. How technically when we talk about group one, it's really 1A. So there's like an A numbering, a B numbering, and on some periodic tables like this one, there's just a straight across 1 through 18 numbering. So there's just different ways over the years that people have numbered the groups. Most of the time in most chemistry classes that you use, like we talked about, we use the A numbering, which again is 1, 2, skip the transition metal, 3, 4, 5. And for anything on the outside of the transition metal region, you want valence electrons, that's the numbering you should go with, the normal 1, 2, skip the middle, 3, 4, 5. But if you happen to come across a question about transition metals and valence electrons, then you kind of have to revert back to kind of in the middle here, like 3 through 12 is sort of what you would want to look at. Yeah. Any questions on that? Okay. All right. So we're going to talk about some periodic trends and why certain things happen with certain types of elements. But first off, metals and nonmetals. A reminder again, when we find these, or where we find these guys, we have that staircase, and to the left of the staircase, right, is our metals. Upper right of the staircase is our nonmetals. And as you go down a group, especially in metals, they tend to give away their electrons a lot easier. So if you go down group one, which is what that little guy is there, lithium, sodium, potassium, rubidium, and cesium, as you go down that group at the bottom there, they're going to give away their electrons super easy. As you go up the group, it's going to get a little bit harder, but they'll still give them away pretty easy, but definitely a lot easier as you go down. The most active nonmetal is actually found upper right of the periodic table. So the most reactive nonmetal up here, the most reactive metal bottom left of the periodic table over there by francium over there in that area of the periodic table. And that has a lot to do with some of these trends we're going to talk about here as to why that is. And let's talk about those trends so we maybe can understand it. The first thing we want to talk about is perhaps an idea known as effective nuclear charge, or Z effective is sometimes referred to. And that's effective nuclear charge. And the idea with this is we'll just take a really simple example to demonstrate it, which is lithium. Lithium has 3 electrons. It also has 3 protons. So when we look at sort of the electron configuration for lithium, it is 1s2, 2s2. I'm doing so bad with numbers today. I know it's been a long day. That's all right. It's my 400th hour lecturing. Let's try this again here. Get rid of that there. That's why they invented erasers, I suppose. All right. There we go. How about a 1? That's 3. I think I should get the calculator out and calculate that. So we got 1s2, 2s1. Now, when we draw like a little picture here, if you will, we have like our lithium nucleus that has a +3 charge because of those protons that are present. We have kind of on the first energy level 2 electrons, right? Our core electrons here, right? And lithium, which is group 1, would have 1 valence electron, right? It would be this guy right here on the second energy level, if you will, kind of floating around randomly out there. So remember that when we talk about the attractive force between a positive charge and a negative charge, it actually increases with the sort of charge magnitude. So something that's +3, for example, and -3 would be held together tighter than something that's like +1 and -1. So as the charges increases, so does sort of the stickiness of it. Well, they kind of stick together a lot harder and tighter. So when we look at these lower level electrons, they are pretty much near the nucleus. So they are actually feeling the full brunt of that +3 charge. So they're like right up front. They got the front row seat. They're feeling the full brunt of that positive charge. So they're going to be attracted to the nucleus really, really strongly. And they're going to be held really strong because of that. And that's why they're actually the core electrons here, because they're going to be held pretty tight. Now, when we get to our lonely valence electron out here, that electron is actually experiencing what is sometimes referred to as shielding. And what I mean by that, it is actually shielded, that outer electron, from the full brunt of the +3 charge. So just a really bad example, but you know, you used to be able to just pick your seat at the movie theater. can't do that anymore, I don't think, right? So you get there early, you get your seat in the middle, nice, perfect looking at the screen. And right before the movie starts, empty theater, but somebody comes and sits in front of you with a big giant hat, right? Now just shielded, right? Half the screen, you can't see any of that. So that's sort of the same idea here. These lower energy electrons are actually shielding that higher energy valence electron from the full brunt of that positive charge. The result of that is that valence electron, which is out there by himself there, is actually feeling a less of an attractive force to the nucleus. You could actually calculate it. If you calculate the Z effective, it is the positive charge from the nucleus, which is +3 because there's 3 protons, and it is how many negatively charged electrons are in its way, and that's 2. So plus minus 2 means that instead of feeling a +3 attraction to the nucleus, that valence electron is actually only feeling like a +1 attraction, which means it's not going to be held as tightly as those core electrons, which are much closer. That also explains why, again, one of the reasons valence electrons are involved in bonding, because they're not held as tightly. They're able to be kind of removed or shared because they're not feeling that full brunt of that positive charge. Any questions on that? Now, the general trend for Z effective, if you take your generic periodic table, which looks like a box, it increases as you go this way, and it decreases as you go this way. And one of the important things to remember, right, if you look at the atomic numbers on the periodic table, which is the number of protons, increases as you go this way, right, to the right. And that means that guys over here have a lot bigger positive charge in the nucleus. So even those outer electrons are still going to feel, even with the shielding, they're still going to feel a pretty good pull in. And that's going to bring everybody closer to the nucleus than you do over here, where you have a less protons in the nucleus, not as big of a positive charge. So they're going to still feel a pull, those outer ones, but not as much as you start going to the right here. They're going to start really feeling a much bigger pull towards the nucleus. Any questions on that there? Now, another really important trend that I just wrote all over, so let me get rid of that there, is ionization energy. And ionization energy is the energy that's required to remove an electron from the gas phase of an atom. And that's what we see here. We have a metal with no charge becomes a metal with a charge, and basically an electron is being given off in this equation on the right-hand side of the arrow. Ionization energy is basically what it happens when we lose an electron. And when we lose an electron, things become positively charged, are cations. So we associate ionization energy with the formation of a cation in this case. Now, electrons actually do come off one at a time. So for example, if we had magnesium, it would have no charge. The first thing that would actually happen is magnesium would just lose one electron. That is what is sometimes referred to as the first ionization energy. Then what will happen is that magnesium with a +1 charge will then lose one more electron and become a +2 charge. And the energy required to do that is what's known as the second ionization energy. Then perhaps the guy with a +2 charge will give away one more electron, become a +3 charge. And that is what is known as the third ionization energy. So every time you drop an electron, there is the ionization energy associated with that. That's the first, second, third, however many electrons you want to give away. If you had to venture a guess, is it easier to remove the first electron or the second? Which one's easier to remove? It's a 50-50 shot. What do you think? It is actually the first one is easier to remove. So let's think about what happens when we lose an electron. We have our magnesium, right? It's got electrons flying around. When it loses an electron, what happens to like the electron cloud? Does it get larger or smaller? Yeah, you lost an electron, so it kind of shrinks, right? And what that essentially now does is those other electrons that are on the outside now find themselves closer to that nucleus, right? Which means it's going to be held tighter. So it's going to take a little bit more energy to remove the next electron. Gets smaller, right? Now we've just moved closer to the nucleus, going to take more energy and more energy. So it takes a lot more energy to remove, say, the second electron than the first, a lot more from the third than the second, and so forth. So the general trend in ionization energy is on the periodic table. For the first ionization energy, it increases as you go to the right and decreases as you go to the left. And between first ionization energy, second ionization energy, and third, it increases every time you take off an electron. That also means that the positive ion, the cation, in terms of its size, is smaller than the neutral guy, right? Because its losing electron is getting smaller as it does that. Any questions on that there? Now, when we think about magnesium, it typically will make a +2 charge because it's in group number 2, but I just showed like 3 electrons coming off of it. Why does it make a +2 if, there's a third ionization energy? Well, if we look at the electron configuration for our magnesium, I'll try to do it right this time. Let's see. We'll go with little 3s2 action. Magnesium is group number 2, which means how many valence electrons does it have? Has only 2, which are these. The rest of them are core electrons, right? Which are, to start with, very close to the nucleus. And now that you just dumped out those 2, they're even closer to the nucleus. Good luck trying to make that happen. It's not going to happen. If you're thinking about energy, maybe, this is like, say, I don't know, these aren't the right numbers, but maybe like 750. Then maybe it goes up to like 1800 or so. Then maybe it jumps up to, 12,000 in terms of energy needed. So it's a pretty big jump as you go through each of those electrons. And at some point, once you reach the core electrons, after all the valence electrons are gone, energy is not energy efficient for that to happen, and it doesn't happen. And that's also why certain things on the periodic table have fixed positive charges, like our group 1 has a +1 charge, or group 2 has a +2 charge, and our group 3 has a +3 charge, because at that point, aluminum's crazy. After the third electron goes, if you want to try to remove that fourth one, good luck. It's never going to happen. It's just too much energy to try to pull that thing off. It's not going to happen because they're too close to it. And again, that's why aluminum just kind of bottoms out at 3 with its 3 valence electrons. Question on that there? Yeah. I'll answer that in a couple of slides. How's that? Yeah. All right. So, and it has to do with kind of what we're talking about here. And so at the end, we'll talk about really why that happens, and what happens to kind of cause that to occur. So ionization energy, again, increases as we go up to the right on the periodic table, down to the left. And again, that is what we talk about when we talk about sort of cations being formed. Another couple of trends that's important is electron affinity. Electron affinity is the energy change when an atom gains an electron. So just like ionization energy is sort of associated with cations being formed, when things gain electrons, they become negatively charged and they're anions. And we associate electron affinity with anion formation, or negative ions. And on the periodic table, it increases as you go up to the right. It decreases as you go down to the left. It's actually the energy change when somebody gains an actual electron. Is it a perfect sort of pattern? The truthful answer is no, but that's the general trend. For example, if you were to look at the energy change for all these guys here in the halogens, you would see as you go up, it increases, then it kind of drops and then goes back up a little bit. So it's not like a perfect trend, but that's the overall trend that sort of occurs. Now, something that is oftentimes confused with electron affinity is another important trend, which is electronegativity. Now, electronegativity is the ability of an atom to bring electrons towards itself. And that, again, is different than sort of electron affinity, which is the actual energy change when they do gain those electrons. Electronegativity is like, I want to like bring electrons towards me. I want to kind of take your electrons if you're near me. And on the periodic table, it increases as you go up and to the right. Fluorine is actually the most electronegative element you could have, and it decreases as you go down and to the left. So going up and to the right, we have things that want to bring electrons towards themselves, which also goes nicely with our electron affinity, which means if they're going to bring electrons towards themselves, they're probably going to gain them. And we're going to see an increase in that electron affinity, right? Affinity basically means that you like something, right? So you like to gain electrons, you typically will gain electrons. Any questions on those? We will see electronegativity more with the bonding in the next chapter as well. But it's a good periodic trend to think about. That goes with atomic size. By the way, when we're talking about gaining electrons, what happens to the ion in terms of size from the neutral? Does it get smaller or larger if it gains an electron? It gets larger, right? It gains an electron. So the negative ion actually is larger than the neutral one because it's gaining electrons to its electron cloud. And then again, it's opposite of our positive guy that shrinks basically as it keeps losing it. Atomic size actually decreases, as you can see, going to the right on the periodic table, and increases as you go down. The reason for that is really all of our trends that we've been talking about. As you go to the right, the effective nuclear charge increases, right? So as we were talking about earlier, even those outer electrons are going to feel a much stronger pull to the nucleus because there's just a lot more positive charge in there. So overall, starting point, they're going to kind of squeeze together. As opposed to the left-hand side here, we don't have as many protons in there. So those outer electrons aren't going to feel as strong of a pull, and it's going to be a little bit larger in terms of their size. Now, if we put together all of our periodic trends here, if I can find it maybe, in a wonderfully drawn periodic table, also known as just, again, a big old rectangle, I suppose. So if we take our effective nuclear charge, which increases as you go up and to the right and decreases as you go down. We take our ionization energy, which increases as you go up to the right and decreases as you go down. If we take our electron affinity, I'll just abbreviate that EA, increases as you go up to the right, decreases as you go down. If we take our electronegativity, increases as you go up to the right, decreases as you go down. And we take our atomic size, increases as you go, I'm sorry, actually that's the only one that decreases as you go up to the right, increases as you go down to the left on the periodic table. So what does this all mean about what the elements that we find on the periodic table, our metals and our nonmetals? If we go up and to the right on the periodic table, that is where we find our nonmetals, right? And as we go up and to the right, we have atoms that are smaller because they have a greater effective nuclear charge. That's going to pull all the electrons in closer to the nucleus, which means it's going to be really hard to try to get rid of those electrons. So it has a very high ionization energy. It also has a very high electronegativity, which means it wants to bring electrons towards itself. And it has a high electron affinity, which means it's successful in doing so. It has a big energy change because it's able to gain electrons. So all of those periodic trends together tell us that nonmetals typically like to gain electrons, right? Now, if we go to the left and down on the periodic table, where kind of our metals are, if you will, we have basically all the opposite trends. We have atoms that are larger, which means the outer electrons aren't close to the nucleus. They're not held as tightly, which means you could just look at them and they'll go away. You don't have a lot of ionization energy, very low ionization energy. They have no interest in electrons. They have very low electronegativity, and they have no interest in gaining electrons. So all of those things for our metals basically tell us what we see with our metals, which is they are typically the ones that will lose electrons because of those periodic trends. They're like, take my electrons, please. To answer your question about why does that happen and things gain charges, when you put a metal next to a non-metal, right, and they come in contact with each other, this guy has, again, all those characteristics of take my electrons. I'm not looking to keep them. I don't want your electrons either. And he's going to be more than happy to transfer his electrons over to the non-metal, which has all of the properties of I'm going to keep my electrons and I'm going to take yours. And I'm going to do that. Yeah. It is in a sense, rust and oxidation is was known as a redox reaction, and really what a redox reaction is, we'll talk about in a later chapter, is this: it's a transfer of electrons, and that's exactly what's happening. Yeah, yeah, no, it's absolutely right. So yeah, so basically any metal that has what's known as a SRP, a standard reduction potential, that's less positive than oxygen, will allow basically oxygen to steal its electrons. And that's basically what oxidation is happening in terms of the metals. Any metal that has like one that's more positive than oxygen, like our friend gold, no oxidation occurs with that. He won't be able to do it. It actually turns around the opposite way. He would want to take the electrons from the oxygen. That's why it doesn't actually do that. But that's actually a real good example. Redox is actually what you have occurring with a metal and non-metal to make an ionic bond. It's actually one of the definitions is a transfer of electrons. Yep. Other questions? That's also why, by the way, this right here will result in the metal becoming positively charged, cation, and the non-metal becoming a negative anion, and they will be attracted to each other through that opposite attraction. No sharing of electrons are actually happening here between those two. That is going to be an ionic bond. And you have no sharing of electrons is basically happening. Yeah. Exactly. That is always the case. Yeah. Yeah. Because the metal has all those properties that we just talked about that they're like, take my electrons, no problem. I'm not going to fight you. You can just have them, basically. The non-metals have all those properties of good luck trying to take my electrons, but by the way, I'm going to take yours, right? So I have no problem grabbing your electrons, and they're going to become more negative. So non-metals, whenever you got a metal and a non-metal together that makes an ionic compound, and where there is an ionic bond, there's no sharing of electrons, but there is this transfer of electron because of these periodic trends. It just perfect situation for that to occur, basically. Kind of like, if we go back to sort of the oxidation of metals, that sometimes it's just a perfect situation for rust to occur. You just need a little bit of water, moisture, and the metal and some oxygen, and it's going to do it by itself, no problem. And that's what's going to happen when you put these two together. This is also why when we're going to talk about in the next chapter, when we talk about what is referred to as covalent bonding, and that is between two nonmetals. So when two nonmetals come together, if you think about where they're located here on the periodic table, they all have the very similar periodic trends. Neither one of the nonmetals want to give away their electrons, right? They both really want to hang on to their electrons and actually take the other person's electrons. But because they are both nonmetals, they have very similar trends, neither one of them are going to be able to achieve taking an electron from the other, like we have with a metal and a non-metal. So what ends up happening in that case, the best that they could do is like, we'll just share, basically. I'll keep part of mine, you keep part of yours, we'll kind of share in between us. Nobody completely loses electrons and stuff like that. And that's why we end up getting a different type of situation happening with covalent bonding, which is a sharing of electrons rather than an ionic bond. Because of those periodic trends, it's just perfect situation for that electron to completely go from one guy to the next. In a covalent one, when we got guys that have similar periodic trends, best they can accomplish is like, we'll just share. Yeah. And nobody's going to completely lose an electron. Nobody's going to completely give away an electron. As we'll talk about in the bonding chapter, that sharing also comes with a limit, in a sense. Sometimes that sharing is like, we'll play nice with each other, equal. And sometimes the sharing is like, I'm going to pull a little bit more, but I'm going to still try to hang on, kind of like a tug of rope, right? The guy's still hanging on to the rope as he gets pulled. He's still hanging on, right? And there's that different degrees in terms of sharing electron that also occurs as well. Other questions on that there? Yeah. Yeah. Yeah, so the definition of electron affinity is actually, the definition of it is actually the energy change that occurs when an element basically, or an atom basically, actually does accept the electron. Now, electronegativity is the atom's ability to kind of get into that situation of being able to drag electrons or bring electrons close to itself, so it's able to basically kind of gain them, if you will. And that's what electronegativity is. So there's a difference between it. You can kind of think of it like this. Electronegativity is like the starting part of that. Like it's going to kind of drag the electrons to it. Electron affinity is like, I just did that successfully. Now I'm getting some energy as a result of actually accepting that electron and gaining that electron. So it's kind of like a before and after, if you want to think about it that way. Electronegativity is like going to pull it towards me. And then electron affinity is what happens when it successfully does that. It's able to gain an electron, the energy change that occurs in the atom. Other questions? Okay. So last thing we're going to talk about here, which is a good little starting point to the next chapter, we're going to talk about bonding, is Lewis dot symbols. And I call them Lewis dot symbols, but nowadays sometimes people will just generically call them electron dot symbols. And Lewis dot symbols are the symbol for an element, and they are really show one dot for each valence electron. And again, valence electrons are the ones that are involved in bonding. And as we just talked about, the easiest way to figure out how many valence electrons, group number, right? So group 1 has 1, group 2 has 2, again, 3, 4, 5, 6, 7, and 8. You don't have to worry about transition metals for Lewis dot symbols or anything like that for sure. And so basically when we do that, we take a element symbol and we use, again, one dot to represent each of the valence electrons that are possible. By the way, there's really not a hard rule on how you should apply those dots, other than a lot of people will go kind of one dot at a time clockwise and then pair them up. The only main rule is no more than 2 per side. Yeah, that's pretty much the main rule in terms of dots. By the way, if I do 2 per side in my picture there, how many total electrons is that? At 8. 8 valence electrons, and bonding is a really important number, as we'll talk about in the next chapter. That is what is known as the octet rule. And that is essentially, no matter what type of bonding you're talking about, ionic bonding, covalent bonding, everybody wants to kind of have that 8 valence electrons. Because on the periodic table, who has 8 valence electrons? The noble gases, as we were talking about with electron configuration. That will put everybody in that electron configuration like the noble gases, which, as I mentioned earlier, is pretty much the whole point of bonding. Both ionic bonding and covalent bonding is for everybody to achieve that noble gas configuration. By the way, the one exception, is we'll talk about a lot because it never hurts to talk about it early, is hydrogen. Hydrogen, by the way, to get to a noble gas only needs to go where? What's the next noble gas after hydrogen? Helium. Helium has how many electrons? Only 2 for hydrogen when we're doing bonding, yes, and that is the reason it only needs to get to helium to get noble gas configuration. Should never, ever, ever, I'll do it 3 more times for good measure, ever, ever, ever have more than 2 electrons. So if you're doing anything with bonding in the next chapter or wherever you're doing it, and you're drawing more than 2 electrons to hydrogen, you should also probably draw an X because it's going to be wrong. Yeah, so it should never, ever have more than that. Everybody else needs to get to, obviously, our 8 here in terms of that, and everybody else wants to kind of get to that 8. So again, if we were looking at sodium, which is group 1, it has 1 valence electron. We're looking at oxygen, which is group 6. It has 6 valence electrons. Again, each of the dots represents 1 valence electron. These electron dot symbols help us draw what are referred to as Lewis structures for covalent bonding. They could also help us, as we'll talk about in the next chapter, understand ionic bonding and what's happening in that case. You should also remember that when you do see a Lewis dot symbol, which, like, here's the whole periodic table I made one time when I was bored. I should get a hobby. It is only the valence electrons that are showed. Yeah. So they obviously, all these guys still have more electrons, except for hydrogen, obviously, but everybody else, and maybe helium, but everybody else has more electrons. They have those core electrons, but typically we use Lewis dot symbols or electron dot symbols to help us look at bonding. And once again, it's those valence electrons that are things that are involved in bonding. Any questions on that there?